Yeah, I got some like reset from the veins. I didn't fall down, so I just escaped it. Huh?
And I'm just like. I get to much more I wanted to, so I took like an hour. I don't know if I feel like there's yeah, I feel like I was seeing crazy. Yeah, it's like what is it? I'm sitting in this object, so what's something? Yeah. I can tell all about how the basketball line.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. All right, so today is another week. It's week 7. Just a reminder, I guess, first thing that our midterm exam was pushed back. So originally it was supposed to be this Thursday at during class, but we pushed it back to Tuesday, March 10th, which is a week from today. Okay. You guys have any questions back there? So today, we are starting something new. So what we start today is not going to be on the midterm exam. So I want to be clear about that. This is kind of starting our second unit here. Which is second unit. First unit, I would say is fairly kind of uniform in message. It's kind of all about differential equations essentially. Second unit is a little bit more hodgepodge, and so we're going to be kind of jumping around to a lot of different things. We're going to be doing vector calculus, some integral theorems, then we're going to jump to something called Fourier transforms. So it is we are going to be jumping around a bit. So this is where kind of 308 kind of jumps off the rails a little bit, but there's just a lot of different topics that we have to cover in this class to get you guys ready for the next ones. Okay. So today, originally this lecture was supposed to be just the lecture before the midterm. So it's kind of chill in nature. So a lot of today is going to be hopefully very much review for you guys. So we're just going to review just very basic vector algebra, things like adding vectors together, multiplying by scalar, dot product, cross product, all things that you hopefully have seen before many times in your mathematical careers. But it's good to kind of just review them and talk about them at least in context of what we're going to be talking about, which is ultimately going to be vector calculus stuff. So things like gradient, divergence theorem, Green's theorem, things like that. Okay. All right. Other announcements. So homework 3, I know is you guys already have turned that in. So I haven't posted the solutions yet, just because the midterm was pushed back. So I do plan on posting the homework 3 solutions probably either tomorrow or Thursday. Depends on when I can get to it. Okay, but it'll be up before the end of the week. Okay. So look forward to that. And then homework 1, homework 2 solutions should already be up there for you to look at for your stuff. Okay. So just a reminder, I write all my problems. So I write all the homework problems in the exam. So, studying the homework problems, redoing them, that is a great way to study for the exams. It's going to be the same style of problems, but on the exam, of course. Okay. And one thing I've kind of been talking with a few students too is that, I write the exams, in a way that is, that you should be able to do everything on the exam in time. you know, I take the exam myself. I have to write the solutions. And so, you know, I test to make sure that the exam is good. But at the same time, you know, you want to be kind of strategic with your time. And so I think one mistake that I see people make a lot is that, you know, the first four questions you'll see on the exam are the short answer questions. You know, I write those short answer questions so that you can answer them in about, you know, maybe 2 to 3 sentences. But sometimes I see people write, you know, like, you know, Law and Order on there. So, you know, because I think some people have the strategy of, you know, I see this topic and I'm just going to write everything that's related to it. And, you know, yeah, maybe you'll get the answer somewhere in there, but you'll have wasted, you know, 20 minutes of your time writing that answer when you have the rest of the exam to do. So, you know, try to be strategic, you know, don't, you know, try to give each question as much time as you need to. Don't be afraid to kind of skip around if you think a question's taking you too long, you know, go to another question and then come back to it. Okay. So, you know, I was telling another student today too, that, you know, what I'm looking for on the exam, you know, with all that said, I do know that it is still a time constrained situation. So, you know, don't get bogged down in the details. And so, what I'm looking for when I'm grading exams is I'm looking at your process, okay? Because that's what we're learning in this class. You know, we're not, you know, yes, it is important to get the answer correct, but at the same time, this is a mathematical skills class. And so what I'm looking for to see is that, you know, did you set up the problem correctly? Are you going to be following the same process, right? Whether you get the exact answer at the end or not is more or less not as important to me. It's more important to me that you are kind of following the process. You're doing things the right way. Okay. And so, you know, I try to be as generous as I can with partial credit. You know, so even if you don't think you're going to get the right answer at the end, you know, at least detail for me, you know, what you would have done. That way I can give you some partial credit. Okay. Okay. Oh, another announcement. So someone looked through my past YouTube channel as well. So, you know, this is not the first time I've taught this class. So in the past, what I was able to do, just because I had more time in the past as a junior faculty, was I actually created like review videos for all the midterm exams. So those should still be up. So actually, if you look through my playlist on EGME 308 on my YouTube channel, you'll see that, you know, maybe at least 1 year prior, I made like an hour-long review video for this midterm. So the content for this class has not really changed. You know, so if you go back to that review video, that might be something that's useful to you guys for study. So I don't have time to do that anymore nowadays, just because there's committee work and advising I have to do. But you know, I would definitely look into that if that's something that you were interested in for the just help you study. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. Okay. So again, you know, the topic that we're covering today is not going to be on the midterm. Okay. But we are going to start a whole section on differential vector calculus. All right. So, you know, the next few weeks are going to be actually quite interesting because, you know, we're kind of going back even further in your math journey. So we're going back, you know, Calc 2, Calc 3 here, right? And I remember, you know, when I was a student and I took things like, I took classes like multivariable calculus, you know, the applications for that didn't really hit me until, you know, honestly, until I was almost graduated, until, you know, I was almost in grad school. So, you know, the whole point of these sections here is to, you know, again, you know, review all these kind of really important vector calculus theorems, all these important concepts from multivariable calculus, but, you know, kind of give them a different, you know, different perspective or different twist to kind of see how they actually applied in the engineering context. Okay. Okay. So the first thing, you know, I want to discuss here is this concept of a field. Okay, so fields are you know quantities that you'll see a lot if you ever get into you know engineering you know analytics or anything like that. Okay, so a field is basically a function of multiple variables. It's a singular field. And so that function, you know, is essentially meant to represent some kind of physical quantity, some kind of engineering quantity of interest that depends on multiple variables, usually multiple space variables. Okay. Okay, and so this concept of a field is used a lot in engineering, right? And so for a lot of the work that I do for my own research, this concept of field is something that I use all the time. Okay, so let me give you an example. All right, so let me actually give you an example from my own research. Okay, so the research that I do is I do computational work in the area of kind of biomechanical engineering, right? Specifically, modeling of blood flow. Right? Specifically, I'm interested in modeling or computations of blood flow in three-dimensional geometries. Okay. Okay. So, for instance, a very common three-dimensional geometry where blood flows in every single one of us is we all have a blood vessel called the aorta. Right. So basically, the aorta looks like the following. So the aorta is basically the first blood vessel that comes from your heart. And so you have your heart here. It pumps blood. The first blood vessel it sees is this kind of candy cane looking blood vessel that kind of looks like this. Okay. Every one of us has one of these. It's it basically takes blood and it goes from your heart. It kind of loops up. You have blood vessels that come off this top arch. These are the blood vessels that go to like your arms and your head. And then the ones on the bottom there obviously go to your lower body, to your legs and your toes and your feet, right? Okay. All right. And so I run simulations on blood flow like this. And so basically, whenever the heart pumps, right, it's going to drive blood through the aorta, right, into all the different vessels that are around. Okay. And so to describe this flow field, right? So to kind of describe this flow, one thing that I compute is what's known as the velocity field. Okay? And what the velocity field tells me is that basically it tells me how the direction and how the magnitude of the blood flow velocity changes as you go from point to point within the aorta. Right? And so the way that we describe it is we say that the velocity is a function of our three spatial variables here, x, y, and z. Okay. So that's a very basic example of field. So basically any engineering quantity or any physical quantity that is going to change based on its position, that is what we deem as a field. Okay. And of course, you can think of other examples as well. So let's look at a thermal example. Oops. So, so that was one thing about my research. So this is one thing about my hobbies. And so, one thing I love to do is I love to cook. And one thing I got into a really deep rabbit hole in over the winter break is fry pans. So I bought myself a new set of fry pans recently. And the science of fry pans is actually fascinating, right? And so one thing that is actually really important, right? So let's say you have a fry pan, cast iron, stainless steel, carbon steel, right? You put it on your burner. One mark of performance of a fry pan is how well it distributes the heat along the surface of the fry pan. Okay. All right, so the way that we can kind of describe that, the way we kind of model that is through a temperature field. Okay. All right, so let's say that you have a fry pan here. Right. And so let's say you have a flame that's coming underneath here. Okay. All right. So usually, usually when you have a burner, your flame is not completely uniform around. There's, you have kind of pockets of, flame which are more concentrated in certain areas, right? And so if you look at a top-down view, right? So your fry pan is essentially, circular, at least for the most part. Okay. And so you can map it out, right? And you can kind of characterize this by saying, you can see where the hot spots are going to be on your fry pan, right? So maybe, you have like a ring of fire, right? So maybe your burner is kind of makes a ring of fire like this, right? So this is obviously where, you're going to have your hot spots, okay? Right? Because that's directly over the fire. But as you go away from it, right, maybe you'll have some spots that are cooler, right? So maybe at the edges, right? It's still going to be hot. So, don't touch it. So this will be, we'll say it's not so hot. Okay. And if you have a good quality fry pan, then, even if you have a burner that does not kind of uniformly distribute heat, the fry pan should do a pretty good job of distributing the heat. Where, if you look at the difference in temperature between the hot spot and the not so hot spot, it shouldn't be that great. Okay. All right, so this is another example of a field where we have some quantity here. Our quantity here is temperature, right? And so we can say that our temperature is going to be a function of multiple variables here. So this is a two-dimensional case. We can just kind of look at this in 2D. And in fact, it's a circular case, right? And so, a lot of times when we think of fields or we think of multivariable functions, we think of, Cartesian coordinates. We think of X, Y, Z. But we can also have polar coordinates. We can also have cylindrical coordinates, spherical coordinates, right? And so for a circular fry pan like this, maybe we use polar coordinates, right? So we say the temperature is a function of the radius or the distance from the center and some polar angle theta. All right, so that's the idea of fields, right? And so, we kind of get away from this notion because, everything we've done up to this point with our differential equations, we've only really looked at one-dimensional functions, right? So functions of a single variable x, single variable times, right? And so those are always going to have its place, right? But if you're going to be doing any kind of, simulation work, computational work, right, you have to be kind of comfortable with working with multivariable functions with this idea of fields. Because that's where all the practical problems are going to be. All right, and of course, these are not the only two examples. These are just examples of things that I'm into. But you can use fields to model all different kinds of phenomena. Okay. All right. Any questions on this so far? Okay. All right. So let's get some definitions. Okay. All right. So the first definition we'll have is what's called a scalar field. All right, so a scalar field is one where we assign a single value, or in other words, a scalar value to each unique coordinate instance, or in other words, to each unique combination of x, y, z, or r theta coordinates. right? So we only have one single value that's assigned to each point. Okay. All right, so we've already seen an example of a scalar field, and so I think the most prominent scalar that we kind of work with as a mechanical engineer is temperature, right? So temperature is a great example of a scalar. Okay. So temperature only has a magnitude, so there's no direction associated with temperature. Things are either hot or cold, right? And so when you talk about temperature field, that is a great example of a scalar field. So there's a single value temperature assigned to every x, y, z, or r theta, r theta coordinate. Okay? Okay, and so another type of field that we have is called a vector field. Now, these get a little bit confusing because we're looking at functions of multiple variables. And so there's x, y, z being kind of thrown around. But a vector field is one where we associate a vector quantity to every single point in space. Right? Right. And so there's multiple ways to characterize a vector. We'll get into it later as well. But I think the most common way and the most I would say mathematically convenient way to express a vector is in terms of its components. And so when we have a vector field, each of the components of the vector field is itself a field point. Okay. In fact, you can kind of treat each component of the vector field individually as a scalar field. Okay. So let me kind of give you an example of this. Okay. So we've already seen one today, the velocity field. So I kind of messed up the notation above. So typically when you have a vector field, we use an arrow to denote the fact that it's a vector, right? So for the velocity vector field, we would have v with an arrow above it as a function of x, y, z. Okay. Now our velocity vector will have its own x, y, z components, and each of those x, y, z components will be functions of x, y, z. And so it kind of gets a bit confusing, but I think once I kind of write it out, hopefully be a bit more clear. Okay. So we can say that our velocity vector field, which is a function of x, y, z, is equal to u at x, y, z, v, function of x, y, z, and w, which is a function of x, y, z. Okay, where u, v, and w are each of the individual components of the velocity. Right, so this u here, x component of velocity. V here is a y component. And this here is a z component. So for mathematical purposes, you can treat each individual component of the vector field as a scalar field. Okay. Now they're not unique to each other. They're not unique in the sense that they're all coupled in a way, right? So the x velocity is gonna change the y velocity, but that depends more on the governing equations. But at least for now, if you have a vector field, each of the components you can consider as an individual scalar field. Okay. Okay. All right. Any questions on this so far? Okay. All right. So the concept of fields, is something that's going to be pretty pervasive for the next, 2, 3, 4 weeks here. Okay. So it depends on how long it takes us to get through this section. Right. So it definitely helps to kind of, be familiar with it. Okay. And, I don't want you guys to just see these as just, it's just multivariable functions. Like, because I think that's kind of what is the sense when you take this for the first time in a math class. Is, they just treat it as, this function just depends on multiple variables. But I want you to think about these functions as, these are actually physical quantities that represent something of engineering interest that do depend on these spatial variables. And, that's basically what's going to allow us to do analysis on these things. Okay, so that's kind of where we're going, and that's kind of what we plan to kind of do. But there is a lot of preliminaries that we need to kind of get up to in order to get to that point. Okay, all right. So let's do kind of a very kind of basic, quick review of vector algebra. So again, a lot of these vector algebra things, you've probably seen before. I hope you've seen it before. But we're just going to review them just for the sake of completeness. Okay. Okay, so let's define vector. I know it feels strange to define a vector after we've talked about vector fields, but let's do that. Okay. So a vector is a quantity that has both magnitude and direction. Okay. And so that's how it kind of differentiates itself from a scalar, where a scalar quantity just has a magnitude, right? So vector has both magnitude and direction. Okay. Okay, so and like I mentioned kind of before, the most common way or the most convenient way to refer to a vector is through its components. All right, and so if we have a vector that's in three-dimensional space, or let's just do two-dimensional space like this, right? Or if we kind of draw the XY axes here, right? So this would be the Y-axis, this would be the X-axis, okay? So the components of our vector V would be basically the projection of this vector onto our principal axes, right? And so if we kind of draw a perpendicular line that goes down to the X-axis, right? And we measure this distance from the origin up into where it crosses the X-axis, right? We'll call this Vx, that is the X component of our vector. Okay? And if we do the same thing on the Y-axis, we basically draw a perpendicular line, or in other words, we project our vector onto the Y-axis. And we measure that vertical distance. We say that is Vy, right? So the way we typically describe this vector is say our vector V is equal to parentheses Vx, comma, Vy. All right, and the same can be said about a three-dimensional vector as well. Just I cannot draw in 3 dimensions, so you'll have to settle for 2. Okay. Okay. All right. So the other, just for trivia's sake, I won't write this down, but the other way that we can describe a vector is through its magnitude and orientation, right? And so we can describe its magnitude as just simply the length of the vector, and then its orientation usually is described by some angle it makes with some principal axis. Okay. So that's kind of like the polar definition of a variable, which has its uses, but I think generally we like to describe vectors by its Cartesian coordinates. That's kind of the simplest way. Okay. Okay. All right, and so right, so if you have two vectors, right, we say that two vectors are equivalent if all of their components are equivalent to each other. And so that means every single one of their components. And so that means, the two vectors are essentially right on top of each other in the XY plane if we were to graph it. Okay. Okay. All right. So very simple so far. Just definition of a vector. Any questions on this? Okay. Okay. Let's do another basic thing. Let's do vector addition. Okay. Right, so two vectors can be added to each other. And so the way we do that is we simply just add their components, each of their individual components together. All right, so for example, right, this is not really an example. This is kind of how you do it, right? So let's say we have a vector A, and it has three components, A1, A2, A3, okay? And we have some vector B. Its components are B1, B2, B3, okay? So if we add these two vectors together, we're still going to get a vector, right? So adding two vectors gives you a same vector of the same size, right? So A plus B is equal to, okay? So we're still going to get a three-component vector, but each component of our new vector is going to be the old components added together, right? So this is going to be A1 plus B1, comma, A2 plus B2, comma, A3 plus B3. Okay. Okay. And visually, what you see when you add two vectors together is that you basically take one vector and add it to the tail, or add its tail to the head of the other vector. And it doesn't matter which you do. So you can, in this case, you can add the tail of A to the head of B, or the tail of B to the head of A. You end up with the exact same result. Okay. All right. So visually, if we plot this out, right? So let's say we have a vector A that looks like this. Actually, let me color code these. Okay. So let's say vector A looks like this. And let's say vector B looks like this. Okay. Right, so we add these two together, right? So we basically let's take B and add it to the end of A, right? Right, so then we get a result that looks like this, right? So in purple here, I have basically A plus B, right? But you can see you get the same result if you take the tail of A and add it to B, okay? Right? Doesn't matter which you do, right? So vector addition is commutative, so it doesn't matter which order you take it in. You're going to end up with the same result, okay? All right, any questions on vector addition? Okay. All right. So next basic operation that we'll do is scalar multiplication. Hey, Scam Likely's calling me again. Okay. All right. So another thing we can do is we can take a vector and we can multiply it by a scalar. Okay. if you've ever wondered why we call them scalars and not just numbers, right? So scalar is just, for a long time I always said the scalar is just a math fancy way to just say a number, right? But the reason we call it scalar is that, if we take a scalar, we multiply it by a vector, we're essentially scaling every component of that vector by that scalar. Okay. Okay. All right. So for instance, right, if we have vector A is A1, A2, A3, right? And we have some scalar C. So C is some scalar quantity. So it's just a number. Okay. So if we take C, we multiply it by A, what we're going to get is C multiplied by each component. So we have CA1, CA2, CA3. Okay. So C multiplied by vector A is CA1, comma CA2, comma CA3. All right, and then visually, what happens is that, with the scalar, we're essentially going to be, modifying the magnitude or modifying the length according to that scale. All right, so let me give you an example of one thing that we do a lot in engineering analysis is what we do is we create what's called a unit vector. All right, so the concept of a unit vector probably is something you've seen before in your previous classes, but the whole idea of a unit vector is one that is a vector that has a magnitude of 1. Okay. All right, so unit vectors are very useful. They're useful in a lot of different contexts. But I would say the most common use of a unit vector is a way to indicate direction, a way to indicate orientation, without adding any scale to whatever you're. All right, so how do we make a unit vector? So the way we make a unit vector is we scale it by the original length of the vector. Okay, so let's say we have some vector, right? So let's say we have vector A, which is A1, A2, A3, okay? Where our vector A here may not necessarily be a unit vector. So we'll say it's just an arbitrary vector of arbitrary. Okay, so if we wanted to turn this into a unit vector, right, we basically need to scale it so that its magnitude is 1 or its length is 1. Okay, so one way that we can do that is we can first compute the length of this vector, compute its magnitude. And so the easiest way to compute the magnitude of a vector is to simply use our distance formula. So it's going to be square root of each component squared of our vector, all added together, right? So we're going to take square root of a1 squared plus a2 squared plus a3 squared. Okay. And so usually we denote the magnitude by these kind of vertical braces, right? Right, so you've probably seen that notation before. So that's typically the notation I use, right? So if you have vertical braces around a vector, that essentially means that that's going to be our magnitude, okay? And so to create a unit vector, right, we're basically going to divide our vector here by its own original length so that we turn the length into 1. Okay, so we are essentially going to take a vector divided by its magnitude. So it's going to be a1 divided by square root a1 squared plus a2 squared plus a3 squared, comma a2 divided by square root a1 squared plus a2 squared plus a3 squared, comma a3 divided by square root a1 squared plus a2 squared plus a3 squared. Okay. So we're taking the original magnitude and we're dividing it through to each component. Okay. And so the result, right, the result of doing that arithmetic there is we get a vector that has the same direction, right? So we didn't modify the direction. We didn't modify the orientation of our vector A. We just modified the scale of each component so that its overall length is 1. Okay. And just a little bit of additional trivia. So and I will say every textbook, every instructor has different notation. But typically when I denote a unit vector, I use kind of a little pointy hat, right? And so usually if I have a unit vector here, I give the vector name A, and I give it a little pointy hat. Okay, so we say that this is A hat. So A hat is a unit vector in the same direction as our original vector A. Okay. All right, so that's one, I would say, very common application of scalar multiples for a vector. Any questions on this? Good. Okay. All right, so let's get into the last couple of things today. And so, next thing we want to review, it's a little bit just rapid fire today, is the dot product. All right, so another name that you'll see for dot product, kind of the original name for the dot product is the what's called an inner product. So some kind of like old school, engineering textbooks will call it the inner product, but I think more modern products are more modern textbooks, modern kind of presentations that we refer to as the dot product. I've always learned it as dot product, but if you ever read textbooks from like the 70s or 80s, they'll probably refer to it as the inner product. Okay. All right. So now the dot product is interesting because it's a vector operation that you perform on two vectors, but the result of the dot product is not a vector itself, it's actually a scalar. Okay. All right, so let's give its definition. Right. So if we have two vectors A and B, so we're gonna use the same definition for A and B as that we've been using. Right. So we have A dot B. Okay. Essentially, what we do with the dot product is we take each of the matching components between those two vectors, we multiply them together, and then we sum them all up. Okay. So it's gonna be A1 times B1 plus A2 times B2 plus A3 times B3. Okay. And so you can see on the right-hand side there, we have a summation, right? So there's quite a few terms, right? But because it's all added together and each of the individual components, A1, A2, A3, B1, B2, B3, those are all scalars, right? So the result on the right is going to be a scalar quantity. All right. So dot products are used a lot in engineering. Okay. There are a lot of different applications, but let me make one kind of comment before we get into the applications. Where I think typically when you learn dot products, you learn it as a vector operation, but you can actually take dot products between two matrices as well. Okay. We're not gonna use it, but I would be remiss to kind of not mention it. Right. So if you get into kind of graduate level solid mechanics, you'll see this notation. You'll actually see dot products between four-dimensional tensors, which is kind of another trip that we won't go down. Okay. But the same kind of property applies where when you take the dot product between two mathematical quantities, you don't get something of the same dimension. You actually go down a dimension. Okay. Right. And so if we think of a matrix as kind of a two-dimensional vector, or two-dimensional vector, right? So the result of a dot product between two matrices is a vector. Okay. Which is one dimension down. Okay. Right. And then you can also take the dot product between two three-dimensional matrices. So we're talking about 3D tensor, right? And so the result of that is a regular matrix. And so the kind of the whole point of this is that a dot product is a dimension stripping operator, right? So it takes whatever dimension of your original inputs, and then the result is going to be one dimension less. Okay. So when you take the dot product between two vectors you can kind of see as like a one-dimensional construct, right? The result is a scalar, which is a zero-dimensional construct. Right? Again, we're only going to use the vector version, but I thought I would mention that in case you do see it in a future class. Okay, so let's talk applications of dot products. Okay, so there is many applications for dot products. So let's start with the most obvious one. Okay, so this is the one I think everyone kind of learns in their Algebra 2 class. Okay. So taking the dot product between two vectors is a very convenient way to determine the angle between the two. All right, so let's say we have a vector A. We say we have vector B. Okay. And let's say that we want to compute the angle between them, right? So as long as A and B are not equivalent or they're not parallel to each other, right? There's going to be some kind of angle that kind of tells you about the difference in orientation between them. Okay. Okay. And so the way we can find this is if we take the dot product between these two, okay? There is a proof and there's a formula that says that the dot product between these two vectors is also equal to the product of their magnitudes. Right? So we take the product of the magnitude of A and the magnitude of B, okay, multiplied by cosine of the angle in between them. Okay. Okay. And so if we solve this expression for theta, right? We just do a little bit of algebra here. We get theta is equal to inverse cosine of dot product of A and B divided by the product of their magnitudes. All right, so I think this is kind of the first thing that you know that you kind of use dot products for, is to find the orientation between two vectors. Okay. Now there are special cases, of course. Now, if two vectors are perpendicular to each other, then their angle is going to be 90 degrees. Okay. Right, so that's what it means for two vectors to be perpendicular or orthogonal to each other. So, okay, and of course we know cosine of 90 degrees is 0, and so cosine of 90 degrees is 0. That means the dot product between the two vectors is 0 as well. Okay, so if two vectors are perpendicular, then their dot product must be 0. And of course, that the logic kind of works the other way too. So let's say that you have two vectors and you take their dot product and you find out the dot product is 0, right? Then you can conclude that the two vectors are perpendicular to each other, or they're orthogonal to each other. Okay. Okay. Any questions so far on dot products? Okay. All right, so another application for dot product is to basically perform what's called a projection. Now, this was a concept that, my math teachers kind of said repeatedly, but I honestly did not understand it until I got kind of further into my engineering career, right? Okay, so let's see if I can do a better job of explaining this than all my math teachers that way. Okay. Okay. So what do I mean by projections? And so, let me once again kind of draw two vectors here. Okay. All right, so let's draw a vector A and a vector B. Okay. Okay. So I think that the term projection kind of comes from the visual kind of understanding or the visual interpretation of what's going on, right? Right. And so let's say that we want to project A onto B. All right, so visually what we're doing is we're essentially casting a shadow. So we're casting a shadow of A onto B, right? So the way we can interpret that is, let's say we draw a perpendicular line. Okay. Right. Going from A to B. Okay. And let's say that we measure this length, right? So that length, right? That length from that projection is equal to our dot product. All right. So where would this be useful? So why would we want to kind of do this kind of weird thing, right? So this is useful when we want to find out, how long or how far is A going in the direction of B. All right, so basically answer the question. right? So how far along B does A reach, right? Because even though A and B here are separate vectors, right? They do have some commonality, right? So they generally kind of both go in the same direction, right? So they both kind of go upwards and to the right, right? They don't exactly go in the exact same way, right? But there is some commonality, right? And the same can be said in the other way too, right? Right. And so if we take the dot product between A and B, that's the same thing as the dot product between B and A, right? So we can kind of ask that same question: how far along does B, how far along A does B reach? Okay. So an extension of this idea of projections is to, basically use this to kind of pick out certain components. Okay. All right, so let me kind of give you a very, very simple example. So let's say that we have some vector A, right? And then what we want to do is we want to project A onto the x-axis. Right, so let's say we have our x-axis like this. Okay. Right, so we basically want to project A onto that x-axis there. So we basically want to find out how far does our vector A progress along the x-axis, right? So to do that, we're going to take the dot product of A, okay? And we're going to take the dot product between A and a kind of a special vector called I hat, okay? Where I hat here is a unit vector that's defined in the same direction as our x-coordinate. Okay, so if we write this out, our vector A, we'll just assume it's 2 dimensions for now. Okay. So our vector A is going to have components A1, A2. Okay. And our I vector here is a unit vector in that direction. So a unit vector in the x direction, remember, a unit vector is a vector with a magnitude 1, right? And so a vector of magnitude 1 that goes purely in the x direction is going to have a value of 1, 0. Okay. Okay, so we say this is very easy to compute, right? So we have A1, A2 dot product with 1, 0. That gives us A1 times 1 plus A2 times 0, which is just A1, right? Which is exactly the x component of our vector A. You might be thinking, wait a minute, it feels like we just went in circles, right? We didn't need to do the dot product to tell you that. You can just look at the vector and you can say that same thing, right? But what if you want to find the component of A in a direction that's not one of the coordinate axes, right? Okay. All right, so let's say that we have some unit vector n hat here, okay? And we have our vector A, right? And we want to find the component of A that's basically in the same direction as n, right? So we want to perform a projection once again. All right, so once again, we can take our A vector and dot product with our n hat, okay? And this will basically tell us the component of A that's parallel or in the same direction as our normal vector n. Okay. All right, so one application of this, is it's one thing that my seniors are kind of dealing with a lot at the moment. So one of the electives I teach is 436, which is computation of fluid dynamics, and so it's a lot of fluid mechanics, right? So one thing that they are doing is that when they compute velocity fields, right, they have to find out how much of that velocity field is crossing between one domain to the next. Okay. All right, so let's say that we have our velocity field, maybe it looks something like this, right? So our velocity field is a function of x and y, okay? And then let's say that we have some kind of domain, right? So, or some domain separation, right? So let's say we have some kind of domain that's denoted by that, where we characterize the domain with some kind of normal vector n, okay? And we want to find out, how much velocity is actually crossing that plane. Right? So the way we do that is we simply just take our velocity field and we dot product with our normal vector. Okay. Right. So this idea of using dot products for projections is all over engineers. We do any kind of work, especially in fluid mechanics, right? Dot products are kind of everywhere. So if you're doing any kind of work that involves vector fields, dot products is going to be everywhere. And so this kind of interpretation, this kind of visual way of thinking of dot products as a way to project or as a way to find components of the vector field in a certain direction, that's kind of very essential to kind of how you understand the theory of these kinds of this kind of physics. Okay. Okay. And by the way, I know all the examples today have kind of had a mechanical engineering flavor to it. I know we have a more diverse audience here, but these are just kind of strictly just from my own experience, just because I am mechanical engineering. I'll try to bring it back kind of in the future. So we'll do more electrical engineering stuff when we get to Fourier transforms. So our EEs can kind of look forward to that. All right. Any questions on this so far? Okay. All right. So last thing I wanted to review today is the last of the, I would say, kind of basic vector operations, is this idea of a cross product. Okay. So cross products is actually something we're going to use pretty soon. So it'll probably come up in the next lecture when we talk about this idea of a curl. But the cross product is an operation you can do between two vectors that gives you another vector. Okay. And so this other vector, this third vector that comes out is kind of unique in the sense that it is guaranteed to be perpendicular to both of the input vectors. All right, so if we define, the cross product of A and B, okay, It's going to give us a new vector v. And the way to compute the dot product, I think the easiest way is to kind of use this kind of 3x3 matrix and take its determinant. Okay, so if we have A cross B is equal to, right? We have a 3x3 matrix here, where the first row is I hat, J hat, K hat. Okay. So I hat, J hat, and K hat, those are all unit vectors in the X, Y, and Z direction respectively. Okay. And then the next two rows are going to be the components of our two input vectors. So second row is going to be A1, A2, A3, and third row is going to be B1, B2, B. Okay. Okay, so this is the way I kind of always learned cross products. You know, there is a formula, and I'll kind of put the formula after this, but I think this is a kind of a nice visual way to do it. Okay, because what we're going to do here is we're going to take the determinant of this 3x3 matrix. Okay, so of course, in order to use this method, you have to know how to take the determinant of a 3x3 matrix. Okay. Okay, so just to kind of refresh your memory, let me kind of show you the way to take a determinant of a 3x3 just very quickly. Okay. Okay, so the way to take a determinant of a 3x3 is you basically go based on the first row, right? And we basically make three expressions based on the entries of the first row. Okay. Okay, so first entry in the first row is an I hat. Okay. So our first expression is going to be I hat. And we're going to multiply that by the determinant of a 2x2 matrix, where the 2x2 matrix is we get that from the original matrix, but covering things in the same row and the same column as that I hat. So what we're going to do is we're essentially going to cross out everything that's in the same row and the same column as that I hat. And then what we're left with there is a 2x2 matrix that we can take as determinant of. Okay, so if I hat multiplied by determinant of A2, A3, B2, B3. Okay. Right, so that's our first expression. Our next expression is going to be based on the second entry in the first row, which is J hat. Okay, and we're going to do the exact same thing. So we're going to basically cover up everything that's in the same row, everything that's in the same column, and then we're going to write that that expression down there. But remember, the second term is always going to have a minus sign. So we're going to have a minus J hat multiplied by determinant of A1, A3, B1, B3. Okay. And then last term is we're gonna do the same thing for K hat. So K hat, we're gonna circle that, cross out everything in the same row, cross out everything in the same column, plus K hat times determinant of A1, A2, B1, B2. Okay. All right. All right, so all that's left to do here is to take determinants of all those 2x2 matrices. And so 2x2 matrix is pretty straightforward, because to take the determinant, we're just going to, product of the two terms on the main diagonal minus the product of the two terms on the off diagonal, right? We should do that. We get A2, B3 minus A3, B2 multiplied by I hat minus A1, B3 minus A3, B1, J hat, plus A1, B2, minus A2, B1, K hat. Okay. And so this formula here, if you prefer to just memorize the formula, this is the formula for the cross product between two vectors. Okay. But I could never remember this formula, and so that's why I have to visually kind of go through the 3x3 matrix every single time. Okay, but if you can memorize this formula, then you don't have to go through the matrix, save yourself some writing, just plug it in. Okay. All right, so you can see from this expression here, right? We get another vector, right? It's not expressed in our traditional sense, but we're basically making use of our three unit vectors here. So this collection of terms here, this is our x component. This collection of terms here, this is our y component. And then this collection of terms here, this is our z component. Okay. And remember, when you're taking cross product, you're always working in three-dimensional space. There's really no such thing as a cross product between 2D vectors. Technically there is, but then you're going to get a vector that's pointing out of the page. Okay. So then how do we determine, which direction this cross product is facing, right? And so the most popular way to do this is to do what's called the right-hand rule. Why is the right-hand rule? Well, I guess the mathematicians who came up with this theory were right-handed, right? And that's kind of how history works. If you're the first to discover it, then you can call it whatever you want, right? Okay. All right, so the way the right-hand rule works, right? And so, I'm going to do my best. And for those of you on Zoom, you'll have to kind of try to do my best to kind of see here, right? So you take your right hand, don't take your left hand. Otherwise it would be the left-hand rule, right? And you're basically going to make your pointer finger, that's going to be one of the vectors. And then your other three fingers are going to point in the direction of the other two, right? So I'm going to use this A vector, B vector notation just because we've been using it. So the A vector here is just whichever vector comes first in the cross product. Okay. I have to remember that, when I'm explaining right-hand rule, I say, you use your other three fingers, right? So don't use your middle finger, otherwise you might accidentally flip someone off. Okay. Right, so your middle finger, your ring finger, your pinky, point that in the direction of the B vector, whichever comes second in the cross product. Okay. And so you do that. The natural direction of your thumb, right? That's going to be the direction of their cross product. Okay. So if you're ever confused about, which direction the cross product is going to be, just simply use the right hand. Okay? You'll look kind of silly. You'll feel kind of silly, kind of, pointing your fingers in kind of weird directions on the paper. But I think there's no easier way to determine the direction. Okay. Now this is important, right? Because whenever you have two vectors, and we're saying that there's going to be a third vector that's going to be perpendicular to both, right? Technically, there are two options for it, right? Right, and so let's say we have two vectors. So let's say we have two vectors in the xy plane here, right? So we have A and B. Okay. Right. So if we take the dot product between these two, technically we can get a third vector, right? One vector that can work is a vector that comes out of the page, right? So that's kind of pointing directly at you. Or another vector that's also perpendicular to both is one that goes into the page. Right. And so the question is, right, which one of these is actually the cross product, right? Because technically both of those into or out of the page is going to be perpendicular, right? So let's use our right-hand rule. I'm going to look really silly doing this, right? And so we point our right hand into, we put our pointer finger in the direction of A, we put the B vector, we put my other three fingers in the direction of B, we can see that the cross product is going into the page. Okay. If the ancient mathematicians were left-handed, then the cross product would come out of the page. But since we're right-handed, we're going. Okay. All right. Cool. Any questions on cross products? Okay, all right. So that's all the time we had for today. So today was just kind of a rapid fire kind of just review of these stuff. Thursday we'll start getting into new stuff. So we'll start talking about gradients and what that means. But we will cross that bridge when we get there. So thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you guys on Thursday.
Thank you. Oh, yeah. Studying SODs, the velocities, versodies, activities.
Yep.
Yep. Okay. Good day.
See you, Anthony.
Yeah. He's like, that might be, that's why I'm like, I'm